Are you able to look at the screen?
Yes, sir.
Okay. Okay, I think we can start now. So, welcome you to the live sessions for the course Basics of Finite Element Analysis Part 2. So, as you may know, the course instructor is Professor Nachiketa Tiwari from IIT Kanpur. This is first week of this live session. So, introducing myself, I am Vikram Balaji. I am a research scholar from the Department of Mechanical Engineering in IIT Madras. So, before going into the session, we'll just see some small details of the live sessions. So there are totally 8 weeks in this course. So there will be 8 live sessions. So spanning 8 weeks, starting from today. So every Monday evening from 6 p.m. to 8 p.m. So this 2 hour session for this live sessions. The Google Meet link. So you might have already received the email regarding this. So once again, I'm highlighting here the Google Meet link is this which is mentioned over here. Uh, these videos, once after the is currently being recorded, once the session finishes, these will be uploaded to the YouTube in this following channel. So I think you will get the link of this video once the video is uploaded in YouTube. So if in case you are missing some, you are not able to attend some session, you can look at this session later in YouTube. So what basically we are going to do in every live session is, so first we will we will do some brief recap of the concepts which we learned in the week's lecture, which will be very brief, followed by solving some of the sample assignment questions. So our main objective is to solve some sample assignment questions so that you will be able to solve the assignment questions of the course. And you will also, if you have any doubt in the week's lecture also, you can able to clear here. So that is, so, and then the discussion of doubts. So this is the objective of the live sessions. So so now we'll go move into the session. So, as you may know, the week one contents you can see here. So, what week one was basically, it was a quick review of the basics of finite element analysis, part one. So, what it involved is basically two things. One is the fundamental principles of FEA. So, this was mainly illustrated through finding the area of a curve and using different types of discretization to find out the area of a curve. So through that, we saw how what is a fundamental principle. That is, there is a domain, and we have to discretize it into a number of finite elements, and then we assume some approximation functions, and then we try to solve the differential equation in a numerical way. So that is the fundamental principles of FEA. In coming to the steps followed in FEA, so as I told, first is the discretization of the domain. Uh, Second is the assumption of interpolation functions. Third is the weighted residual integral. Fourth one is the weak formulation of the weighted residual integral. The fifth is assembling the element level equation. So once weak formulation is done, you will get some equations at the element level. So those element level equations have to be assembled to get the global equations. So once the global equations are done, then we need to apply the boundary conditions. So this is the week one contents. So this so we through the assignment questions we'll try to recap what we learned in this week one. So now we will start proceeding to the assignment questions. Just a minute. Okay. So these questions will be in MCQ. Some questions will be MCQ and some will try to solve live. So first we will see some set of MCQ questions before going to solving some problems. So this is the first question. FEA, which is finite element analysis, can be used to solve. So some options are given. So first option is boundary value problem. Second option is initial value problem. Third is eigenvalue problem, and fourth option is all of the above. So, which of the following can be solved through FEA is the question. So, do you know the answer for this? If you know, you can answer.
Sir, I guess all of them.
Yes, all of the above. Okay. So yes, you are right. All of the above. So if you would have observed if you would have attended the first part, the basics of finite element analysis first part, then there we would have seen different types of problems which can be solved by FEA. So in that we would have seen there are initial value problems, boundary value problem, and eigenvalue problem. So all of these can be solved in the finite element method. Okay. So this was about question one. So let us now go to the second question. So which of the following statement is true about finite element analysis? So we have four options. First option is residue obtained equals zero. The second option is the solution obtained is exact. Third option is the solution is exact at boundaries. Fourth option is it is an analytical technique. So which of the following statements is true? So only one option is true. So can you guess which option could that be? Any guesses?
Sir, yes, the solutions are exact. I don't know.
The solution. Oh, so which option B or option C?
Option B.
Option B. Okay. So let us see. The answer is actually option C. So why it is option C means, so when we are doing a finite element analysis, so there is a variable which we need to solve. So for that we are assuming a certain interpolation function or what you can call shape functions. So whatever solution you obtain, it will not be exact. It will be only approximate. Since the interpolation functions are themselves simplified functions, only one thing we are ensuring is that due to the application of boundary conditions, we can say that the solution will be exact in the boundaries. So, for example, you would have seen in the lecture itself. So, when we are trying to calculate the area under a curve, so one of the exact solution is to just integrate the function within the limits within the given limits. But if we were to do a finite element, then we need to split the domain into multiple elements and then use an approximation for each element and then find out the area by adding all together. So we can see that the solution, it might be exact at some times, but you cannot be sure that it will be exact all the time. So most of the times it will be the solution will be approximate, which will be close to the required solution. However, we can say that the solution is exact at the boundaries since we are applying the boundary conditions, and that's how our functions are also we are assuming in that way. So any doubt in this question? So why is it so? The answer?
No, sir. No, sir. No, sir. Yes, sir. No,
Okay.
sir. No doubt.
Okay. So we'll now go to the next question. So, in finite element analysis, an interpolation function represents, so first option, change in variable over an element, change in variable over the whole domain, shape of the element, and shape of the whole domain. So, what does an interpolation function represents? What is it used for? So, can you guess which option it is?
I guess, sir, shape of the element we're considering.
The shape of the element. Okay. So any okay. So anybody else who wants to guess? So let me see how many people are there. Okay. I think the Chinta sir, I think your mic is switched off, so that's why I'm not able to hear anything.
Yes, sir. Okay. Following, sir.
Yeah, yeah, okay, follow. So
Yeah.
any guesses
Here
and
some
to
disturbance are there.
okay, fine,
Okay.
fine, fine.
I'll check it. Right,
No
sir.
problem. Okay. So okay, one guess was shape of the element. So we'll see the answer now. Answer is actually option A. Change in variable over an element. So let us see why this is. So what is happening is, let me try to use pen. So suppose, as I told earlier, let us say we are having a curve. So what we are interested is to find the, so like this. So this is some f of x. Let us say. So this is my y and this is my x. So we want to find the area of this curve within the given limits. Let us say. So the exact solution will be this shaded portion is going to be my integral of this function f of x. Yes. Okay. So I'm going to have this f of x dx. So this is the area under the curve, and I am going to integrate from, let us say, from 1 to 2. So this is my 1, this is my 2. So let us say I'm going to integrate from x1 to x2. So what happens is, if our f of x is a very complicated function, then we cannot directly perform this integral because the function is complex. So what we are doing as an infinite element is essentially, so let me say, we are splitting this curve into smaller elements. So like this. So we can divide into how much ever elements we want. So at each element, we are going to assume how the f of x is going to vary. So if my f of x is going to be linear, so suppose, let's say it will be some a1 a plus b times of x. So if it is going to be quadratic, means I'm going to assume like this: a plus bx plus cx square. So how this f of x is varying? So this f of x is nothing but y. So this y variable, how it is varying over this thing? That is what is represented by the interpolation function. So these are all interpolation functions. So in this domain, maybe I can assume it's linear or quadratic, or it can be even non-polynomial. So I can assume some, suppose maybe some sine function or cos function. That also I can assume. But usually we restrict ourselves to polynomial functions. So actually, it does not have anything to do with the shape of the element. So suppose if you are having like this, so it could be any differential equation, and you want to solve in this domain means, suppose your element is like this, and you have some differential equation like this, d by dx of some constant a into du by dx. So let us say that there is a u is our main variable, and it varies along x, and this is my some differential equation d by dx of a du by dx is equal to 0. So this x will vary from this one, so maybe from 0 to L. So 0 less than x less than L. So this is how the element, I have split the element into 4. So this is my 1, this is my 2, this is my 3, and this is my 4. So at each element, I am going to assume how the u is going to vary. So we can say that it represents the change in the variable over an element. So at each element, how my u is going to vary, that I am going to represent as a function. Either it could be linear or quadratic. However, if you see the shape of this thing is constant. It's like a say, one-dimensional element. So this is not going to vary. So so is there any doubt why answer is A and not C?
No, sir.
Okay. So you have to remember that interpolation function represents the change in the variable. So how this variable is going to, how we are going to approximate this variable in each element. So that is what the function of the interpolation function. So we'll go to the next question now. Okay. So you might have come across this integral, some error into w into d omega. So omega, we can say it's a domain equal to 0. So this is your is one of the important key functions in FEA. So let me admit. So this is one of the key methods in FEA. So any idea what this W represents? There are four options. One is the coefficient, second is weight function, third is the error function, and fourth is a residue. So any idea?
Sir, weighted function, sir.
Yes, correct. So this is called as weighted residual integral. So this error, we can also call it as residual. Both are same. So as we know, first we saw that the steps in FEA is first you have to discretization of the domain. Once the discretization is domain, then we have to assume the interpolation function at each element. Once we assume the interpolation function, then we have to substitute this interpolation functions in the variable and then calculate the error, or we can call it as residual. So we'll see how to do this in subsequent questions. We'll see how to calculate these things and all through an example. But for now, you can say that error and residual both are same. And this error, instead of making it as 0, what we are doing is we are doing a weighted residual integral. So which means that this error or the residual is multiplied with some weight function w, and it is this weighted residual is then integrated over the whole domain, so across the element. So like this, when we do, we get some equations, and these equations we are going to assemble and then solve it. So this w is nothing but weight function. So I hope there's no doubt in this question. So we'll go to next question now. So which of the following is not true? So there are four options. The natural boundary conditions need not be enforced in the weak form. Approximation functions can be chosen more flexibly in the weak form. Weak form weakens the differentiability requirement on the weight function. Fourth option, weak form weakens the differentiability requirement of the primary variable. So which of the following is not true? So three options are true, one option is not true. So can you identify which option is not true? Any guesses?
So I guess C weak forms doesn't affect the weight function. C.
Okay, C. Okay. So anybody else wants to guess the answer? Whether it is C is correct or is it any other, whether option C is correct or is it any other option? Any guesses? Okay. So we'll now proceed to answer. Answer is yes. Option C is correct. So we'll see each option. So natural boundary condition need not be enforced in the weak form. Why this is true is, so when we are going to solve the finite element, we can see that this natural boundary condition is automatically taken care of through the uh, this thing weak form. So what happens is we do not need to separately enforce the natural boundary condition. It is automatically taken care of in the while solving the weak form. So option A is true. So approximation function can be chosen more flexibly in the weak form. So why this is also correct is, so if in the strong form, if you see the differentiability requirement of the is higher compared to the differentiability requirement in the weak form. So we can choose more number of functions in the weak form. So for example, if your differential equation is second order, means in the strong form your function also will be second order. But once you get to the weak form, you can say that we are reducing the differentiability, because of which you can use even a first order function, which is linear function, in the weak form. So option B is also correct. So between option C and option D, the weak form weakens the differentiability requirement is true, but whether it reduces the differentiability requirement on the weight function or on the primary variable. So which is correct? So actually, weak form weakens the differentiability requirement on the primary variable. So so let me go to this uh, thing. So here I have some note I can easily write and show. So let us say that we have some differential equation. So are you able to see what I'm writing on the screen?
Yes, sir.
Yes. So let us say again the same differential equation, d by dx of some a into du by dx is equal to 0. So what we are going to do in this thing is, so let us say this u we assume some function. So later we'll see how we are going to assume. Let us say it's some uh, g of x or something. So or you can later we'll see how we are going to assume the this thing. So we are just going to see. So what is happening is, this is du by dx. So when we are multiplying with weight, so w into d by dx of a du by dx into dx is equal to 0. So here you can see that the weight function is there, and here you have the, here u is differentiated once and twice, two times. So if you convert this to weak form, so we'll see how we are going to convert later, but you will see that it will appear something like this, some a times dw by dx into du by dx into dx. So this thing we will see in further examples. So this we will do, but you can see that when we are converting to some weak form, you can see that the differentiability requirement, here there was no differentiability requirement for w, and here there is differentiability requirement of first order. Here it was for the primary variable. So one thing you have to remember is u is a primary variable and w is a weight function. This is question 5, I think. Okay. So du by dx, here there is only one time, here two times, this is one time, here it is 0. Differentiability requirement is 0. So if you see the weight function, actually the differentiability requirement is increasing by 1. But if you see same for the primary variable, the differentiability requirement is decreasing by 1. So if you go back to the question, you can see that the weak form weakens the differentiability requirement on the primary variable, but it is not the same case for the weighting function. So answer is C. So C is the false option. So any doubt? So why the answer is C? So we'll see how we are going to do the weak form in this thing. But uh, are you able to understand why the answer is C and not D? So any doubts?
Sir, yes. No, sir.
Okay, okay. So the exact how we are going to do that integration, those things we will see in subsequent questions. But just we can learn that the weak form is weakens the differentiability on the primary variable and not on the weighting function. So this is question 5. So this is question 6. If a domain is discretized into n one-dimensional elements of mth order, so can anybody say what is the order of an element? So if my suppose let us say I'll draw here only. So suppose this is my element. So I have two nodes, 1 and 2, and it's a linear element. So what is the order of this element? Can anybody say? So okay, let us not go into order. So whether it's a or I can say the same element, I'm going to do like this. I'm going to introduce a node in between. Okay, I think somebody. Yes, let us submit. Yes. So this is also one element, element number 1. Here only one element, but I have another node in between. So this is also element 1. So it's not two elements; it is one element with extra node. So this is which one is linear, which one is quadratic? Can anybody say? Okay, somebody has messaged. First one is linear. Okay, correct. Yes, first this is a linear element.
Two node is linear, sir. Three node is quadratic.
Yes, correct. So this is a linear element. This is a quadratic element. So why this is linear means the variation of the primary variable will be behave in a linear fashion in this thing. But because when you have two nodes, if you are going to use a interpolate function with the two data points, the maximum you can come up with is a linear linear polynomial. So when you are using three data points for interpolation function, then you can come up with a quadratic polynomial. So this is a quadratic element. So linear means its order is 1. Quadratic means it is a order 2. So mth order means, so cubic element, let us say it will be like this. We'll have two nodes in between the n nodes. So this is 1, this is 2, this is 3, and this is 4. So what will be the order of this element? This is a cubic. So order will be, so we saw that two noded element is order 1, three noded element is order 2, then four noded element means cubic element, what is the order?
3. I mean, m minus
Yes.
1.
Yes. So m minus 1. So if you have m number of, if you have the mth order means you will have m plus 1 nodes. Yes, okay. So this will be m plus 1. Mth order means m plus 1 nodes. So linear means two nodes. But this is only for one element. So what I am having is I have n elements of this. So I think I will go to this thing. I will better I can write as this thing. So let me use this. So as we saw, this is a first order. This is just one element. Same way, this is also one element. This is a second order. So this is a third order. So if order is equal to m, number of nodes per element is m plus 1. So up till here, I think there is no doubt. But now I'm going to say, let us say I'm going for a second order. So I have two elements, that or I'll say three elements. How I am going to do is, this will be my one element. I'll say another color. This will be my second element. Okay, I'll erase. Just say I select yellow color. This is my third element. So totally how many nodes are there? So we saw that if it is a second order means uh, there will be three nodes per element. So if we have three elements, what will be the number of nodes? So here actually it will be 1, 2, 3, 4, 5, 6, 7. 7 nodes. So how the 7 nodes occur means, so three elements into number of nodes per element, let us say it is 3. So this will be 9. Then you have to minus the two nodes which are common. So how many common number of will be there? So if you have three elements means number of nodes which are common to two elements, it will be 2. So 9 minus 2, 7. So if I have to do it for m m order, n elements. So this is a number of element. This will be number of nodes per element. So this will be n into m. So number of elements into m minus, what is this? 2. So how we got 2? So three elements means there are two nodes common. So if I add one more element in the end, let us say. So this is my fourth element. So it will be, there will be one more node which is common to two elements. So four elements, 3. If it was just three elements, there are two common nodes. So what will be the term which you are going to add here in this thing? For let us say there are this thing n elements.
Sir, n minus 1.
Yes, n minus. Okay. Uh, so what we saw is mth order and n elements. Okay. So if we calculate this, mn minus n plus 1. So this will be okay. So this you understood, right?
Yes, sir.
Ah. So this is the answer. So let us see once more. So first order we have this much, second order, third order. So you understand what is the order. So second order. Yes. Oh, actually I made a mistake in this. Can you identify? So in this somewhere there is a mistake. Any idea where the mistake is? Any guesses? Whether it is this first term or second term, somewhere the mistake is there. So if you are not guessing, no problem. Actually, we saw it is a m order. So if there is m order means number of nodes per element will be m plus 1. But here we just directly multiplied with m. So what should replace this m? This should be actually m plus 1. So yeah, are you guys confused or is it okay? So let me write once again. So we have m order. So m order means n elements. N elements into number of nodes per element. It will be m plus 1. So here we are actually dealing with the second order element. So here three elements. Here three is the number of node element which is 2 plus 1 actually. Second order element. So second order there are three nodes. So then we subtract this by it is n plus 1 I think. Is it n? Sorry, n minus 1. So is it okay or shall I explain again why we are doing this? Is it okay? Why how this occur?
Yes, sir. Yes. M plus 1
Ah,
only. Yes.
yes, yes, m plus 1. Okay. So if I multiply, it is mn plus this will be again n, then minus n plus 1. So this n will cancel. It is mn plus 1. So let us see this whether it is correct. So it is a m order n elements. So let us say we are going for a first order for simplicity, and n elements, four elements. First order means it's a two nodes. One element will have two nodes. So if I'm going to stack four elements together, one, two, three, four. So here one, two, three, four, five. So total number of nodes one mn plus one. So m is equal to first order one, n is equal to four. Four elements. Four into one plus one, which is equal to five. So we are getting five nodes, and this formula turns out to be true. So okay, we'll again verify for some other thing. Second order, four elements. Second order means this will be my one element will have three nodes. So this is my first. Let me take another color. Second, third, fourth. So how many are there? One, two, three, four, five, six, seven, eight, nine. So let me see. We have second order four elements. Four into two plus one. Mn plus one. 8 plus 1, which is equal to 9. Yes, we got 9 nodes. So If you go to the PowerPoint, answer is option D. So any doubt in this question? How we got this?
No,
So,
sir.
okay. So we have to understand what is order. So if it is a first order means it will have two nodes. It's a linear element. If it has second order means it's a three. Uh, Three nodes, it's a quadratic element. Fourth, third order, four nodes, it will be a cubic element, and so on and so forth. And we have n elements of mth order arranged together, then total number of nodes will be mn plus 1. So, okay. So this is seventh question. So for the equation k into u is equal to f. So this is a standard FEA equation where k is your global stiffness matrix, u is your primary variable, and f is your vector. So that vector f contains what? So option A stiffness terms, option B force terms attributable to the distributed external load, C is primary variable term, and D is a terms attributable to the presence of external concentrated as well as distributed loads. So any guess as to what would be the answer? So vector f, k into u is equal to f. So what does the vector f represent? Is it first of all a stiffness term or a load term or a primary variable? If it is a load term, then if it is whether it is just an external load, whether it's just a distributed load or a concentrated load. So we have four options. Any guesses?
Sir, not sure, sir, but I guess B, distributed external load, or
Okay.
maybe D. I don't know.
Okay. So actually answer is D. So if you see actually what will be the equation means, you will have if you in the lecture also sir might have told. So when you have something like k into u, so you will have two terms actually. Here I have represented as capital F, but this in reality it will be some small f plus some q. So this will be force due to distribution, and this will be the point loads. So if you club these two together to make it into one vector means it will have both the distributed loads and the point loads. So yes, it is a load term, but it is a load attributable due to external concentrated as well as distributed. So let us say we have some one dimensional bar like this. So distributed load means you'll have some forces like this, and point load means we'll have something here at the end or maybe in the middle if you are to some f, or it could be this direction. These are the point loads, and these are the distributed loads.
Sir, we cannot see the note.
Oh, sorry. Okay, I'll erase one and I will again write. So let us say you have some bar. So we have split maybe some into 3 points. Here, let us say some F3 is some F3 is acting. At this point, let us say some F2 is acting this way. Other than that, you have some distributed load throughout. So this will be small F. So this F will be this is a distributed load. These two are concentrated load. Due to application of F3, F2, there will be a reaction force also. It will be this direction or this direction. So this F1, F2, F3 all are concentrated loads. This F vector, it is due to both F and Q. So force due to distribution as well as point loads. So any doubt in this why it is both?
No, sir. Yeah.
Okay. So this is question 7. Let us go to next. So here I would have seen that Ku is equal to F plus Q. So as I have mentioned in the note, so this is the thing. This F plus Q here I would have given as a single vector. So which means it is understood that it is a sum of F plus small f plus small q. So in this entire equation, natural boundary conditions are incorporated in which of the following matrices? Uh, think this- okay, we have four options. So again, I'll repeat question. For the matrix equation, K into U is equal to F plus Q. Natural boundary conditions are incorporated in which of the following matrices? So option one is K, option two is U, option three is F, option D is Q. Any idea where the natural boundary conditions will be incorporated? So any idea what is natural boundary condition? So okay, so what are the two types of boundary conditions which you encounter in FEA? Once you see the you would have, if you have seen the lecture, you might have known. So there are two types of boundary condition. One here natural boundary condition is mentioned. What is the second? Any idea? Any guesses? So there are two types of boundary conditions.
Essential boundary conditions.
Yes, correct. Essential. Okay. So essential boundary condition and natural boundary condition. What is the difference? So any idea? What is the difference between essential and natural boundary condition?
Essential boundary condition, I think, sir, imposed by ourselves, while the natural boundary conditions arises itself in the equations when we are solving the uh, equations with the help
Yes.
of weighted residual methods.
Okay. Yes, it is correct. One more thing actually is essential boundary condition is essentially means the boundary condition is directly applicable on the primary variable. So suppose we have the bar means so there the displacement of the bar is our primary variable. So let us say it is u. Okay. I'll again go to this note. So same this thing. So this we have the bar. So let us say this is for 0 to L, uh, and this is, let us say that the displacement is u. So this is x direction. So you have to find what is u of x. So if I say that, let us say the differential equation is d by dx of some constant a into du by dx is equal to 0. So if I mention u of 0 is equal to 0 and u of uh, L is equal to 1, something like this means these are essential. Why means I am going enforcing this u at these points at the boundary. So these two are the boundary points. Here displacement is 0. So if I say that a du by dx at x is equal to 1, like that, is equal to some value 0 or something like that, this is a natural. So essentially, if you see, essential boundary condition directly deals with the primary variable and we have to enforce it. And this a du by dx at s is equal to 1 is equal to 0, this thing, this will actually occur in the equation when we solve the weighted residual method. This will be directly a consequence of the weighted residual method. So this is not enforced. This will rather, it will occur naturally. So that's why it is called as natural BC. So with this in mind, so natural boundary condition will be with respect to this a du by dx. A du by dx at a endpoint. Let us say x is equal to L. So this is nothing but if we see in the A du by dx. So if you see actually A is equal to your Young's modulus into area of cross section usually. So du by dx is nothing but your strain. So strain into Young's modulus into area. So this is actually stress. Strain into Young's modulus. The stress into area will be load. So this load actually I am mentioning at x is equal to 1. So load at x is equal to, sorry, this will be x equal to L. X equal to L. So load at x equal to L, if you see here, means it will be point load or distributed load. Load at a particular point. X is equal to L. At x equal to L position, the load is specified. So it is a point load or distributed load. Any idea? I'm mentioning at a particular location means it's a point load. It will be the either this one or this one. But this A du by dx at x is equal to L is a point load. Okay, so now this is a point load. So once you know that, which of the matrix will take care of point load? Is it K or U or F or Q? So just last question we saw, right? So which of the natural boundary condition are incorporated? Natural boundary condition, it in our case it comes out to be the point load. In for the case of the bar, for any other case it will be some other thing. So in our case, the point load in which matrix are we accommodating? Is it K or U or F or capital Q? So actually, if you see the note, we saw here in the last question, F and Q. So F is force due to distribution, Q is the point load. So answer is Q. So this you would have seen in the lecture also. So any doubt why answer is Q? Any doubt why this, or is it? Shall I explain once more? Is it okay?
So can you explain that? No, sir. Yeah,
Yeah.
the point load. How is it point load?
See. So let us say that now our differential equation. So usually when you have a bar, so there will be some loads like this. These are the distributed loads. Let us say that there is the axial load which is distributed across the length of the element 0 to L. And here let us say that we are applying some point load F. So what the equation will be is minus of d by dx of EA du by dx is equal to maybe you can say is equal to some F. So this F is nothing but distributed loads. So how this comes means, so we saw that EA du by dx is actually load. Last, so here we have seen, right, EA du by dx. Du by dx is strain. EA is Young's modulus into area. Strain into Young's modulus is stress. Stress into area of cross section is your load. So basically, what we are trying to mean here is your F is nothing but load per unit length. This f is nothing but your load. This is your load. But what we are doing is when we are EA du by dx, when we are specifying at one particular point at x is equal to L. So we are specifying only at one point. So this becomes, so here we are mentioning that at EA du by dx at x equal to L is equal to f. So this is how the boundary condition is specified. So this is nothing but your point load. So if u of 0 is equal to 0, let us say that it's fixed. So this is a essential. This is a natural. So natural boundary condition means because a point load exists, so automatically EA du by dx at x equal to L becomes your point load. Any doubt?
No, sir.
Okay. So this is just due to the boundary condition. So we can see that these f terms will occur in this F matrix, and this related to this point load, it will occur in this Q matrix, distributed load. Okay. So this is 8th question. So 9th question. Okay. So we have a differential equation. So which of the following is the correct expression for elements of the f vector? So here we saw ku is equal to f plus q. So when you do this weighted residual integral and then you apply the weak form, then you will get many terms. So what will be the nature of this f term? Will it be A or B or C or D? So A essentially means that you are multiplying the Q with the psi, which is a weight function. So here in B you are multiplying U with the weight function. In C you are multiplying this constant C with the weight function. And in option D you are multiplying A with the weight function. So which of the following will be the correct expression for the elements of the F vector? So do you remember how the weak form, after applying the weak form, how it will be? So any idea of what will be the answer? Or shall we try to solve it?
So it may be A Q upon Q multiplied by point load. I mean weighted function.
Yes, weighted function, yes. So yes, you are actually correct. Answer is A only. So actually, when you are multiplying this entire thing, what will happen is, so if I again go to my notes, let us say what was our question? Minus d by du by dx plus u is equal to q. So into du by dx plus cu is equal to q. So when we are going to do this, we have to bring all terms into one side, minus d by dx of a into du by dx plus cu minus q. So this is your error. So why is this error means here a is not the exact u. U is not the exact function, while it is going to be some maybe u is equal to summation of j is equal to 1 to n uj into psi j. So this is how we are going to assume the variation of u. So if you substitute this into this differential equation and bring all terms to one side, you will see that this will be the error. This will not be exactly equal to 0. If this u was exact, then this will be 0. If u is not exact, we are going to approximate, then there will be error. This error, we are going to multiply and integrate across the domain for the element. So let us say this will be our element means. So this is A, this is B. It's just a linear element. So from XA to XB, this is how we are going to do. So when we do this, then this is when we apply the weak form, how this will become is, this will be, let us say, A into dw by dx into du by dx minus some this will be some boundary term. Then you will have cuw dx, and then you will have qw dx in the right hand side. If I take this to that side, means xa to xb. So this will go in your, this will be a natural boundary condition. So this will go into vector q. So these two will come into k. So if you see, it will be, you can say k into u, and this q, if w I'm going to write it as psi I, because that is how we are assuming in the FEA, wherein if you are going to use an interpolation function psi j, then psi I will be your weight function. So both w and u will be same functions. So if I write psi I, what will become this term means, this will be q into psi I into dx. So if I say it's for a particular element E, then I write the superscript xa to xb. So this will go into my f vector. So this is the answer. So any doubt?
No, sir.
Okay. So I hope you have seen the first week lectures. And is there anybody who has not attended? Is attending? This is as you know, it's a finite element part 2. So part 1, is there anybody who has not attended or at least seen the videos? Is there anybody like that? So if I think if there's anybody like that, then you might be difficult to follow these things, because most of these things he has done, the sir has done in part 1, and part 2, the first week he has given the recap. So maybe if you see the week 1 lectures also, you can somehow get these things. So anyway, for this question we have seen answer is A. So, okay, this is a simple question. Question 10. Let us say stiffness matrix. So, how is the stiffness matrix it should be? Option A, it is a non-symmetric and square. Option B, it is a symmetric and square. Option C is non-symmetric and rectangular. Option D is a symmetric and rectangular. So, any idea what is the answer? Stiffness matrix and the K matrix.
It's B, sir. Symmetric and square. Diagonally, it
Yes.
must be symmetric. No?
Yes, correct.
Symmetric and square.
Yes, symmetric and square. So so we can say that it is symmetric, and if you see this thing, so since it is symmetric, it should also be square matrix. So which means that if it is a n, means it will be as a n cross n. So number of rows and number of columns will be same. Because of it, it is a square matrix, and on top of that, it is also symmetric, which means that across the diagonal elements, if you see, let us say if there is k1 2, it will be equal to k21. In other words, k ij will be equal to k ji. Okay. So this is simple question. Answer is B. Okay. So what will be the size of the global stiffness matrix? So here we saw it is a n cross n. So that n will be whether it is a number of nodes, or it's a degree of freedom, or elements, or coordinates. Any idea? Size of the global stiffness matrix?
First three nodes, yeah, degrees of nodes, yeah, nodes, sir, nodes.
Okay,
NOD is nodes, sir.
nodes. Okay,
Global stiffness.
yeah.
Degrees of
Okay,
freedom.
okay. One option is degree of freedom. Okay. So
No, no.
actually, we'll see
Okay.
one kind of
Tell
example.
me. Nodes means one, two,
If it
three,
is
yeah, one into one.
just a simple bar means, so this is two elements, one and two. So here it is your primary variable is only u. So if you see this, you will have one matrix k11, k12, k21, k22. So this will be one this thing. If you see this, it will be k11, k12, k21, k22. So this will be with 2. So because it's a second element. So if I'm going to combine means, you can say k11, k12, k21, k22, and here you will have the other elements. This will be 0, be 0. So this is your diagonal element. This will be k12, k21. This will be 0, 0. So this is 3 cross 3. So here we see that number of nodes is 3, but number of degrees of freedom is also 3. So degree of freedom means it's u1, u2, u3. So these are 3 DOFs. So in this case, we have degrees of freedom also same, nodes also same. But is it always the case? Maybe we can say it's a beam problem. So let us say we are applying some load. So this is, let us say we are having three nodes. Okay. 3 nodes, 2 elements. So at each node, you have actually 2 degrees of freedom. So one is u, and another is slope theta. So same thing, u1 du by dx at 1. So this will be u2 du by dx at 2. So this will be u3 du by dx at 3. So here what will be means, your u matrix will be u1 theta 1, u2 theta 2, u3 theta 3. Here it was only u1, u2, u3. So if you multiply this, you have to multiply only with u1, u2, u3. But here we have 6. So what will be size of k? So here we have 6 means. So this will also should be 6 cross 6. So how we got 6 means 3 nodes into 2 degrees of freedom per node, per element, which is equal to 6 DOFs totally. So what are the 6 DOF means? U1, theta 1, U2, theta 2, U3, theta 3. So answer is degrees of freedom. So any doubt why it is degree of freedom and not node? So in our case, in linear bar means we have one for each node only 1 degree of freedom is there. So that's why it was 3 cross 3. But here it will be 6 cross 6. So
Sir, here first fixed na first node, then degrees of freedom will be cutted. No?
which one?
3 nodes are
Uh,
there. Okay, for the
yeah, yeah,
beam, for the beam.
yeah, yeah.
First at the first node, it is fixed, no, sir.
Yes, it will be, yes,
Then
that
degrees
we
of
are
freedom
going.
will be cutted.
So yes, that is true. But I'm just telling that is after applying the boundary condition. So this will be before applying the boundary condition. So that's so.
Acha. So better
Uh,
concentrate on degrees of freedom. That's what.
yes, yes, yes.
But
But
as per
if I
your shown figure, I think
it
2
is,
will be
yes,
reduced. Only 4 degrees of freedom.
yeah. But if we say we don't know what is the boundary condition, so let us say some. It could be you are applying some moment, some. So we don't know what is
Hmm.
this moment value, and we are just keeping like this. So then you will have all the degrees of freedom are active in that case. So here you will have 6 cross 6.
Okay.
So as you pointed out, yes, if you suppose if u1 is 0 and the theta 1 is also 0, this is
0,
fixed
0.
beam means,
Hmm.
so this first row
4.
and this thing will be cancelled.
Column.
Second row it will
First
cancel.
one. Yeah.
Similarly, first
Elimination.
column, second column also will cancel. So this will be a 4 cos 4. And these things only will be the required thing. But if you have a general beam with where we do not have
So,
there is no constraint, fixed constraint or anything like that. In that case, we have the 6 DOFs. So in this case, you have to say
yes, sir.
it's a degrees of
Okay.
freedom. Okay.
DOF. DOF.
Yeah.
Degrees of.
Degrees of correct.
Okay.
Okay. So yes. So okay, so this is a, you can say it's a one-dimensional one-dimensional bar, you can assume. So for the figure given below, which of the following statement is not true? So let us go to note. So if I'm going to have like this, I'm going to replace 1, 2, 3, 4. So this is my element number 1, element number 2, element number 3. So the small u, suppose if it is a j, if it is I, something I like this means I is nothing but element number, j is nothing but node number, node number for local. And if I write is equal to capital U something means some k, I'm writing means here k is the global node number. So how to write local node and global node means, so 1, 2, 3, 4, these are global. For local means for each element I'm going to write. If I assume just one element is going to exist means for this element, this will be my node number 1, this will be my node number 2. For second element, this is my node number 1, this is my node number 2. For third element, this is my node number 1, this is my node number 2. These are all local. So which means you, let us say 2 of 1, which means second node of first element, second local node of first element. So this is the meaning. So with this in background, you can you say which one is not true? So if this is U1 means this is first node of first element is global U1. This is one thing. In second statement, first node number of second element is U2 global. Third statement is U2, second node of third element. The displacement of second node at third element will be U3. Fourth statement is displacement of second element, second node in first element is U2. So one of these is not correct. So can you identify which one? So you have to remember local numbering and global numbering. So these are all global. This RHS is global. Here, if you see, these things are local. And the top is element number. So can you identify which one is wrong? So something is wrong. So we'll see the statement one by one. So first node of first element. So what is that? So here we have first element. First node of first element is 1. So is first statement correct or false?
It is correct.
Yes, it is correct. So let us go for second. So first node of second element. So this is second element means in second element my first node is 2. So first
It is
node of
also
second
correct.
element is U2. Yes, it is also correct. So let us go here. Uh, Second node of third element. This is third element. In third element, this is my first node and this is my second node. So it is 4. So is this correct or wrong? Second node of third element.
It is also correct.
Is it correct or is it wrong? Because the second node of third element is we underlined that it is a fourth because this is my third element and this is my first node of the third element. This is the second node of the third element. So second node of third element corresponds to U4. So here it is U3. So is it correct or wrong? This should be wrong. So let us see D option. U2 of 1 means second node of first element. So this is again, let me take a different color. This is my first element. In that, this is my second node. So U2 of 1 is also U2. So this is also correct. So any doubts in this question? So you have to understand each element. The left side will be the first element local number. Right side will be second element, second local number of the node. But in the global, it will be 1, 2, 3, 4. So any doubt in this?
No, sir.
Okay. Answer is C. Okay. Again, so for the same thing, one dimensional bar, four nodes and 3 elements are there. So one of the statement is false. So option A is size of the global stiffness matrix is 8 cross 8. B option is size of the global primary variable is 4 cross 1. The size of the global force vector is 4 cross 1. And size of local stiffness matrix will be 2 cross 2. So let us say that I have only one primary variable u. This is a one-dimensional bar. So we do not have any, it's not like a beam problem where you have another primary variable like slope. So only u is there. So what is which of this following statement is false? Any guesses? What could be the answer? Any guesses? So okay. So let us see each option one by one. The size of global stiffness matrix is 8 cross 8. So here we saw that there are 4 nodes and there is only one primary variable. So which means that each node has only 1 degree of freedom. So totally there are 4 degrees of freedom. But I have mentioned here that size of global stiffness matrix is 8 cross 8. So will it be 8 cross 8? You just saw, right? The size of the global stiffness matrix will be equal to the size number of degrees of freedom.
Not
Is it
true,
not?
sir. It will be 4 plus 4.
Yes, it will be 4 cross 4. So this is okay. We have found out the answer, but let us see other option also. The size of the global primary variable is 4 cross 1. Yes. Why is it 4 cross 1 means? I will go to the notes. It will be, in this case, 1, 2, 3, 4. So my primary variable will be u1, u2, u3, u4. So it is a 4 cross 1. size of the global force vector. Force vector also you can say it will be F1, F2, F3, F4. Global force vector. Actually, this will be nothing but F1 plus Q1, F2 plus Q2, F3 plus Q3, F4 plus Q4. So this is the global force vector. This is also 4 cross 1. So this F is nothing but, as I told earlier, it's a combination of uh, the distributed load and concentrated load. Other option is size of the local stiffness matrix. Local stiffness matrix you will have only 4 cross 4. Sorry, 2 cross 2. So it will be K11, K12, K21, K22. And this will be U1, U2. So this will be for a particular element. Because at one element for local means you have only 2 nodes. If it is node element 2 also you have 1, 2. Same way for element number 3. So when you are then in the global only 1, 2, 3, you will have like this 1, 2, 3, 4. But in the local you will number it as 1 and 2. So for each element you have a 2 cross 2. So this is also correct. So which means option A is the false. So option A is the answer. So we'll go to next question. So this is a numerical, not a numerical, it's a analytical kind of question. So derive the Lagrange interpolation functions for a third order one-dimensional element based on interpolation properties. Use the local coordinate x for simplicity. Okay. Before going into the question, so let me ask one simple question. So let us say that you have a node, you have an element with 2 nodes 1 and 2. So we are going to uh, assume the weight functions. So psi 1 is equal to psi 2 is equal to. So u will be nothing but summation of, so it is not a weight function, it is going to be a interpolation function. So j is equal to 1 to n summation uj into psi j for the particular element. So if n is equal to 2, which means a linear. So if it's a linear means first order, so number of nodes are 2. So this will be u1 psi 1 plus u2 psi 2. All will be with respect to E. So when I have a quadratic element, n is equal to 3. So it will be u1 psi 1 plus u2 psi 2 plus u3 psi 3. Okay. So like that, same for cubic also. So in linear, what is psi 1 and psi 2? Any idea? So if you say this is the length of your element, He, and this is your local coordinate x bar. So this will be x bar is equal to 0, this will be x bar is equal to He. So what is psi 1 of x bar? Psi 2 of x bar. Any idea? Do you remember what is the formula? Any guesses? What is psi 1, psi 2? Or do you want to derive psi 1 and psi 2? How you get that? So if you remember the formula, then you can tell, or you can, if you want to derive, we can derive it. Okay. Leave psi 1, psi 2. So let's say that this is my 0, this is my He, this is my x bar, this is my psi. So what will be the value of psi 1 at this, at x equal to 0? X bar is equal to 0. What will be the value of psi? and at x equal to h, what will be the value of psi? So it will be 1 and it will be 0. So it will move like this. For psi 2, this will be psi 1. For psi 2, it will be exactly opposite. Do you remember this with respect to the approximation for interpolation function? So why is it like this? Okay. Should I derive how the expression, or shall I just write the expression? Psi 1, psi 2. First I will write it, then I will, if you want me to derive, then I will derive. So psi 1 of x bar is equal to 1 minus x bar by he. Psi 2 of x bar is equal to x bar by he. This is do you remember this formula, psi 1, psi 2 for a linear element? What psi 1 and psi 2? Is this okay?
Yes, sir.
Yes. So this you remember, right? So similarly, the question is, what will be for cubic element? 1, 2, 3, 4. So you have 4 points, and this is only a single element. So it is not the 3 elements. We say cubic, third order 4 nodes, cubic element. Okay. So how to derive psi 1? Similarly, we have psi 1, psi 2, psi 3, psi 4. We have 4 psi. So your u is nothing but summation j is equal to 1 to 4 psi j uj, which is nothing but psi 1 u1 for this element plus psi 2 u2 plus psi 3 u3 plus psi 4 u4. Okay. So before going to the psi, so here we saw that psi 1 is here we saw that psi 1 at node 1 is equal to 1. So uh, psi 1 at 0 is equal to 1. Psi 1 at he is equal to 0 for single element. So 1, 2. So this is 0 and he. So yes. But psi 2 at 0 is equal to 0. Psi 2 at he is equal to 1. So how it come means, in this formula you substitute x is equal to 0, you will get answer as 1. So if you substitute x is equal to he, then answer is 1 minus 1, which is 0. So that's how we got this. So 1, 0, but psi 2 it will be 0 to 1. So that's why this graph. So I hope this is okay. So how to derive for cubic element? So this is our question. So same thing if we extend, let us say psi 1. What will be the psi 1 at this point? And what will be the psi 2, psi 1 at rest of the other points? So basically, psi 1 will exist only at x1. So it will be value of 1 and it will go like this. Let me use some other color. So it will be 1. At second location, it goes to 0 and it remains 0 for up to 4. For psi 2, it is going to be 1 at this point, and rest of the points it will drop to 0. like this it will be. So this is 1. For psi 3, it will be 0. Both will be 0. At third position it will be 1, and fourth position it will be 0. At last it will be like this. So basic thing is psi I at jth node will be 1 if I is equal to j, and 0 if I not equal to j. So this is nothing but you would have heard about this. This is the delta ij, Kronecker function. So which means if I and j are equal, then you will have 1. If I and j are not equal, you will have 0. So which means psi 1 at first node will be 1 at first node, and it will be 0 at the other nodes. So node number, this will be 1, 2, 3, 4. So for so up to here, any doubt? First of all, so this is the nature of the interpolation functions in FEM. Is it okay?
Yes, sir.
Yes. So why it happens means, so let us say that you have, what is u at first node? It's simple, it's u1. But how we are assuming it is summation I is equal to 1 to 4 uj psi j, which means that u1 psi 1 plus u2 psi 2 plus u3 psi 3 plus u4 psi 4. So when this is going to be equal to u1, this implies it is possible only when psi 1 is equal to 1 and rest of the other are 0. So then automatically this satisfies u at first node is equal to u1. So what is u at second node? Again, if you write u1 psi 1 plus u2 psi 2 plus u3 psi 3 plus u4 psi 4. If you go like this, this will be 0. Psi 1, psi 2, psi 4 will be 0. Psi 2 is equal to 1. Therefore, it will be u2. So that is the nature of this graph. It will be 1 at second node. At rest of nodes, it will be 0. So what is psi 1 in terms of x bar means? You can say that this is some constant c1. This is a unknown constant into, or you can say x bar minus 0, x bar, sorry, not 0. So before this, I have to draw this thing. So equally spaced. If you assume that all nodes are equally spaced, if your length of the element is h, so this is going to be h by 3. This is also going to be h by 3. This is also going to be h by 3. So if I were to plot the local x bar means, here it will be 0, here it will be h by 3, here it will be 2h by 3, and here it will be h. So we saw that psi 1 will be 1 in this position and 0 in other positions. So some kind of psi 1 of x bar is equal to c1 into these things means, if substitute x bar is equal to h by 3, then what is the this thing? What is psi 1? If I put h by 3 in this formula, if I put psi x is equal to h by 3, x bar is equal to h by 3, what will be the answer of psi 1? It will be 0, right? Any doubt?
Yes, sir, it will be 0.
Yeah, it will be 0. Same thing, if you put 2h by 3, it will also be 0. If you put h also, it will be 0. So this function is satisfying our criteria. What we need to find out is the value of that constant c1. Basically, your function of psi1 of x bar is having 0 at h by 3, 2h by 3, and h. So this is a cubic function that will solve this criteria. So how to find c1? Substitute x bar is equal to 0. What is psi1? It is equal to 1. We just saw here, right? Psi1 is 1 at the first node, and it is 0 at the rest of the node. So at x bar is equal to 0, your psi1 should be 1. So if you substitute this c1 into, if you substitute 0, this will be minus h by 3, this will be minus 2h by 3, this will be minus h is equal to 1. So what is this answer? C1 into minus 2h cube by 9 is equal to 1. Is it correct? Yes. So C1 is equal to minus 9 by 2h cube. So now psi1 of x bar will be C1 minus 9 by 2h cube, x bar minus h by 3, x bar minus 2h by 3, x bar minus h. Is it okay?
Yes.
So similarly, you can also find psi, right? So psi2, if I this thing, so if this is my element, 1, 2, 3, 4, this will be 0, it will be 1 here, it will be 0 and 0. So same thing, I'm going to put psi2 of x is equal to some constant c2 into x bar minus 0 into x bar minus, so this will be 0, this will be h by 3, 2h by 3, h, x bar 2h by 3, x bar minus h. So why I put 0, 2 by 3 and h means at these locations my psi is 0. It is now same thing, if you put psi2 of h by 3, it will be equal to 1. So if I substitute it, c2 into h by 3 into minus h by 3 into minus 2h by 3 is equal to 1. So what is going to be my answer? C2 into 2h cube, 2h by 27 is equal to 1. C2 is 27 by 2h cube. So if I put psi2 of x, 27 by 2h cube into x bar minus 2h by 3 to x bar minus h. So this will be the interpolation function of psi2. So similarly, we can calculate psi3 and psi4 also. So since it is, I think now since I have explained what is psi1 and psi2, you can calculate psi3 and psi4. So we'll go to next question. So I hope it is okay, right? So how we are calculating psi1, psi2, psi3, psi4? Is it fine?
Yes, sir.
Yes. Okay. So I'll go directly to 15. So this will be our last question for today. Actually, I planned one more question, but it looks like we'll be able to complete. So since there's 20 minutes remaining, I think. So we'll just look at this one question. So solve the differential equation. So I'll write this in the note. Minus d square u dx square minus u plus x square. is equal to 0. So what we are going to do, so 0 less than x less than 1. So our boundary is defined. X is equal to 0, x is equal to 1. So we have to use mesh of 4 linear elements. So 4 elements means 1, 2, 3, 4. So like this 4 elements are there. So again let us assume, so for each element, so u is nothing but summation j is equal to 1 to 2 uj psi j. So why j is equal to 1 to 2 means, so we have 4 linear elements. So our elements are linear, not quadratic or cubic or any other thing. So as we tell, step 1, this was the discretization of the domain. So our question told that we have to use the mesh of 4 linear elements. So because of that, we discretize the domain 0 to 1 into 4. So if, yes, so what will be the thing means, it will be 1 by 4, 1 by 2, 3 by 4 and 1. So this will be the location. So each element will be of length 1 by 4. So this is step 2. Step 2 is for each element approximation function. So what is my UE going to be? U1 psi 1 plus U2 psi 2. And what is psi 1? 1 minus x bar by he. Psi 2 is x bar by he. So till here any doubt?
No,
So
sir.
first step we have discretized the domain. Second step, for each element we are assuming approximation function. So we are interpolating function between u1 and 2. So for each element this will be valid. Just that we are now in operating only for the local element. Then while assembly we have to do for assembly. So for that, this for each element. Step 2. What is 3 is weighted residual integral. So I'm going to integrate minus d square u dx square minus u plus square into w into, so this is going to be 0 to h. So what it means, length of the element 1 by 4. So unless for each element we see the node will be 0 to 1 by 4. This element length is 1 4, 0 to h into w is equal to 0. So this is the weighted residual integral. That is a weighted error integral. Okay. So now how we are going to do this? So this will be dx. I can write it as d by dx of du by x. So I'm going to write it the same way, 0 to h. I forgot to add dx. So this is the weighted residual integral. Why dx means I'm across x I'm integrating. So 0 to he. So minus d by dx of du by dx into dx minus integral 0 to h u dx plus integral 0 to h x square dx. So and I have to multiply w everywhere. Into w into w into w is equal to 0. So this thing. So today I have w. So I'll take the minus sign outside. Minus of 0 to h w into d by dx of du by dx into dx. So I'm going to integrate the parts. So it's nothing but integral of w sub dv. So where d is equal to du dx. So w dv, here of w dv is equal to we minus integral v dw. So I'll do the same thing. So minus integral 0 to h e w to dx of du by dx into dx is equal to, so if you do this minus here, this will become minus and this will become plus. So this will be integral and this will be from 0 to h. Integral 0 to h v dw du by dx, this is v to dw by dx into dx. And you have boundary term minus w into du by dx from 0 to h. So this we have found out. Now this we are going to substitute here. So 0 to h du by dx dw by dx into dx. Then this term I will take it to the right hand side. Let me write the other terms. Minus 0 to h u w dx. And I will now write the right. If I take the right hand side, this will become positive. W du by dx from 0 to h e. Then you have this term plus minus x square w dx from 0 to h e. Okay. So till here, any doubt? We have just iterated the parts and we are writing like this. Yeah, any doubt till here?
No, sir. No, sir.
Okay. So now u I am going to substitute summation j is equal to 1 to 2 uj psi j delete, and w is equal to psi I. So substitute. So integral 0 to h d by dx of summation j is equal to 1 to 2 uj psi j into d psi I by dx, w psi I into dx minus u will be summation again uj psi j into w will be psi I dx 0 to h is equal to w du by dx, which means psi I into du by dx. Let us keep it as du by dx for time being. He plus minus x square psi I dx from 0 to h. So if I simplify this, what I will get is, I will combine these two terms together. So integral from 0 to h, I can take the summation outside. J is equal to 1 to 2 d psi I by dx into d psi j by dx into uj into dx. I will bring this inside, rather minus. I will bring this inside. Same thing. Psi I psi j uj into dx is equal to psi I du by x at 0 to h. I will expand du by dx d by dx of summation j is equal to uj psi j. This is at 0 to h plus integral 0 to h minus square psi I dx. So this, if I further simplify, I get uj common. So what I will get is summation j is equal to 2 integral 0 to h d psi I by dx into d psi j by dx minus psi I psi j into dx into uj. So this term is nothing but kij. So this will be to the right hand side. Psi I into psi a summation j is equal to 1 to 2 psi I psi j, sorry, psi I into d psi j into uj from this are boundary plus integral 0 to h minus x square psi I dx. So I also range from 1 to 2. Since there are two nodes, there will be two interpolation function as well as two weight functions. So any doubt here?
No.
Okay. So we have achieved this equation. Now what we have to do is, so we will totally have four equations. Sorry, two equations for each element. So we'll see this boundary term. Summation j is equal to 1 to 2 psi I d psi j dx uj. Or let me give psi I into du by dx. We can keep like this. Okay. Then we have to remember that psi 1 is equal to 1 at x is equal to 0. This will be 0 at x equal to g. Similarly, psi 2 will be 0 at x equal to 0. This will be 1 at x equal to h. So this is our the last time. Right? So if we follow this, then what will happen? So if I put I is equal to 1, then it will be summation j is equal to 1 to 2 psi 1 d psi j by dx uj 0 to h. So if I expand this, it will be psi 1 d psi 1 by dx u1 he 0 to he plus psi 2. Sorry, this will be psi 1 d psi 2. This is for I equal to 1 u2 from 0 to he. So psi 1, if it's put at he and 0, psi 1 at he will be 0. So this will be ruled out. So you will have essentially minus d psi 1 d psi 1 by dx into u1 at 0. Because if I put he, psi 1 at he is 0. This one. So this will be like this. And this will be, if you put psi 2, x bar by h, okay. U psi 1 e. Psi 1 will be, again, it will be 1, it will be u2 into d psi 2 by dx into u2 at 0. This will all be minus. Because at he, psi 1 is 0. So if you put I equal to 2, same thing will become d psi 2 by dx at, sorry, d psi 1 by dx into u1 at he plus d psi 2 by dx u at g. Because in both these cases, I equal to 2, you put, sorry, I equal to 2. So psi 2 will be, this will be 2. Psi 2 will be 0 at x is equal to g. Sorry, psi 2 is 0 at x is equal to 0. So both 0 will be 0 and you will have the edit term. So this is boundary term. So if you put this as k j, so essentially you will get k I j into u j is equal to f plus q. So what will be this k I j? So let us see k I j. This is nothing but this one. Integral 0 to h d psi I by dx d psi j by dx minus psi I psi j. So dx. So this is k I j. So let us put k1 0 to h d psi 1 by dx d psi 1 by dx minus psi 1 into dx. So what is the psi 1 is 1 minus x bar by h. So d psi 1 by dx. So x bar x both are, let us say, interchangeable in this case. So what is, it will be minus 1 by h. So if you do that, 0 to h minus 1 by h into minus 1 by h into minus of 1 minus x bar by h the whole square into dx. 3x bar, let me put it this way. So this will be 1 by h square integral 0 to h dx bar minus 1 minus x bar by h the whole square dx bar from 0 to h. So this will be 0 to h 1 by h minus 1 minus x bar by h whole square into dx. So if you integrate this, so let me expand it. 0 to h 1 plus x bar square by h square minus 2x bar by h. So 1 minus x, a minus b also formula applied. So this will be 1 by h minus integral. So we'll get integral dx x h plus 1 by h square into h cube by d minus 2 by h into h square by 2. So if I multiply this, minus h plus h cancels. So h square h. So 1 minus h minus h square x cube by 3 x square by 2. Okay. So this will be 1 minus h 1 by h minus h by 3. So this is k1. So similarly you can find k1 to k21 and k22. So since it is already time, so so this k11 is there without how to, it's just iteration. You have to just substitute what is I1. In kj you put I is equal to 1 and j is equal to 1 and just substitute here and derive it. So finally you get kj into uj, uj is 1, u1 to u2 and u for the local limit, and then you assemble to get the total. So is this fine up to k1, k11?
Yes, okay, one.
Okay. I think we will stop here since it is already done. So you can maybe try out this, and maybe in the next session we can see what is the exact answer. So you can note this question. So minus d square u by dx square minus u plus square is equal to 0. So we just derive k11. Similarly, you can derive k12, k21, and k22. So these are the local. So maybe only k12 I will try to do now. Rest of the two we can try and we'll verify next class. Next session. So k12 is I just have to put I is equal to 1 and j is equal to 2. So which means integral 0 to h d psi 1 by dx into d psi 2 1 comma 2. So it will be d psi 2 by dx minus psi 1 psi 2 into dx. So what is, so this is minus 1 by h into minus, this will be 1 by h.
Sir, the note.
Sorry. Yeah. So this will be integral h into dx bar. So why this is 1 by h means psi 2. Psi 2 is this one. Where is that? I think psi 2. Yes. So psi 1 is 1 minus x bar by h. Psi 2 will be x bar by h. So if you differentiate this with respect to x bar, you will get 1 by h. So this is the thing. And minus integral 0 to h psi 1 minus x bar by h into x bar by h into x bar. So this you get minus 1 h into h minus integral 0 to h x bar by h minus x bar by h x bar. Minus 2 minus 2 plus. This is also 0 to h. So minus 1 by h, this will be minus 1 by h square by 2 plus 1 by h square into h cube by 3. So this is minus 1 by h, this will be minus HE by 2 plus HE by 3. So this will be minus 1 by HE minus HE by 2, if I put 6, minus 3 HE plus 2. This will be minus HE by 6, I think. Yes. So this is K12. And K21, since due to symmetry, if you evaluate, you will find the same thing, minus 1 by HE minus HE by 6. So K12 is equal to K21. And K22, if you try to evaluate, it will be side to side to side to side. You will have uh, integral 0 to H 1 by H into 1 by H into h bar, then minus x bar by H into x bar by H into dx bar. So psi 1, psi 2, psi 2 into ts. So this will be 1 by H minus, this will be 1 by H square into square x H by 3, H cube by 3. So this is 1 by H minus H by 3. So this was 1 by H minus H by 3. So K11 and K22 will be the same. So if you do for local stiffness matrix, we have something like this: 1 by He into 1 minus 1 minus 1 1 minus H by 3 H by 3 H by 6. Let's say we have 2. So this 3 by 2 1 1 2. This is K elliptic. So till here I have. So I think we will stop here. So we have found out the local stiffness matrix. This will be the same for all the elements because H is going to be same, and this will be same for all the elements. So He is nothing but 1 by 4 because we split the element ranging from 0 to 1 into 4 parts. So 1 by 4, 1 by 2, 3 by 4. So for each element, you are going to do from 0 to 1 by 4. So here also locally, if you see, it will be from 1 by 4 to 1 by 2. But in the local terms, it will be 0 to 1 by 4 in the x bar coordinate. So this will be the same thing. So any doubt here?
No, sir.
Okay. So I think we will stop here. Maybe the exact solution we may not be able to solve because it's already done out. So I just told you how to find out the matrices. And maybe next class we can next session next week we will try to see the solution. So anyway, I'll upload this video in YouTube also. So for the people who are not attending the session, they will be able to attend. So today we have 50 questions. So we saw 15 questions, and I hope this year you will have some concepts and how to solve some sample questions. So I hope this session was useful. So any general doubts or if there is no, we can close the session. So shall we close the session?
Sir, sir.
Okay. So we will see next week. Same time 6 to 8. So we will discuss the sample questions related to V2's lecture in the next session. Okay. So see you in the next week. Thank you. I'll close the session now.
Thank you, sir.
Okay. Bye. 0 to 1 by 4. C is equal to 1.